So this is the second part of lecture 8, and we are going to talk about boosting, bagging, and random forest. Okay, so that's the three things that we are going to talk about. Basically, the references are our book, and if you are interested, like in inference with random forest, there are two nice papers. I'm not going to cover it in the video. So if you are interested, and if you can take a look at the slides and have an appointment with me. We can discuss over office hours or even our live session on Friday. Okay. So as I mentioned to you, the trees are very unstable, right? And the idea is that because of the tree is like this nested sequence of splits. If you make a different use it instead of using, for instance, variable x0 to define the first split, you pick another variable x1. The full sequence of splits can be totally different. Okay, so small changes in one split can make a completely different tree. So the trees are very unstable. So although they are interpretable, they can small changes in the sample can make a huge difference in terms of tree construction. So is there any way to overcome this problem? Yes, there is. There are two ways. Basically, we can use like boosting and we can use bagging. And bagging will, when we use bagging, we are going to have the so-called random forest. Okay. So basically, the boosting algorithm is exactly the boosting algorithm that we saw a couple of lectures ago, replacing a linear model in each step. We replace instead of using a linear model as a weak learner, we are going to use a regression tree. Okay, and it can be, does not to be a fully grown tree, can be a small tree, a simple tree, because remember, we are combining weak learners, right? So we are going to initialize our function by minimizing some cost. You can just take the simple average, okay? And then we are going to, for each iteration, we are going to compute the negative gradient of our loss function, okay? We are going to fit a regression tree for this derivative, that if we use square laws, remember that this gradient will be just the error or the residual of the previous term. Okay, so we fit a regression. Okay, then we compute a value of c, this constant here, just to adjust the model, and basically we are going to update our estimated function at step m will be the function estimated at the previous step plus the step size, okay, that we have already discussed when I talked about boosting with you, plus a new tree. Okay, a tree. This is like a regression tree. Fitted to RTM. Okay. We continue like this, and our output function will be the function, estimated function for f capital M, what's the maximum number of steps. Okay, as simple as that. So we replace a linear learner by a non-linear learner, but a very simple one, a simple tree. Okay. For square laws, the derivative will be just the error. Okay, what's the right size of the trees? Simple strategy: keep the size of the tree fixed at every iteration and make it small. Okay, the larger scale, of course, the larger will be the interaction among different variables. Okay, and so for example, if k equal to 2, there is no interaction. Why is that? Can you know why? If k equals to 2, there's no interaction. Question for the live session on Friday. Okay? We will discuss this on our live session. Okay? Typically in empirical work, we are going to have K between 4 and 8. Okay? And what are the values of M and U? Use the learning rate, something between 0 and 1. Rule of thumb here, not pre-specific, like, doesn't really matter. If you make it too small, it will take more steps to converge. If it's too large, it will be less steps, but it's something that you're going... Usually, if you don't bother about computer time, make it small, okay? So you are going to do more shrinkage. You're going to need what? More steps, okay? And both nu and M will control the prediction risk, okay? And they do not operate independently. If you don't have like a fixed M, the smallest nu, the larger should be M. So some people advocate like to play around with these in the cross-validation, or like monitor in an early stopping. What's the idea of early stopping is that you split your sample into 2 parts. You are training here, but you are monitoring your error here. So here, as you increase M, your error is decreasing, okay? But here in the validation set, it will decrease, but suddenly it will increase again. So when it starts to increase, you stop. And then you really test out of sample, okay, to see if you have good generalization. Okay. So let me show you an example with California housing. Okay, data is available from Carnegie Mellon. Okay, the data set consists of more than 2,000 neighborhoods in California. Okay, and the dependent variable is the median house value in each neighborhood. Okay? And we have predictors like median income, average occupancy in each house, longitude and latitude, average rooms, average bedrooms. These are the variables. Okay. Here in this example, it's really small data. We have just 8 predictors and all numeric, but you can have like really, really large data sets. Okay? And the authors, because there are some outliers, instead of using the square laws, they use like the Huber laws, where it looks like a square function near the origin, but for larger values it penalizes less than the square function. So you have some here, you have a linear function, okay, and not a square function. They selected the tree depth equals to 6 and the learning rate as 0.1. Okay? And that's the derivative of the Huber laws. It comes from the subgradient, as in the lasso. Okay? And that's what they found in terms of absolute error. As the iteration grows, you see that both on the train set and the test set, there's kind of a stability. After a certain amount of boosting iterations, the algorithm converges. Okay? And they show the relative importance for the model because they have a tree in the end, so they can compute the relative importance. So basically what determines the price the most is like the median income, then followed by like 3 variables that kind of tie, latitude, longitude, that's basically a location in the California, the closest to the ocean and closest to the like the Los Angeles area, San Francisco area, San Diego area. Okay, you have larger prices, and of course how many people live in the house is also important. Less important like the population and average bedrooms or average rooms. Okay, so this gives kind of a sense of which are the variables that are more important, but does not give an idea of how nonlinear is the model. So here we have like partial dependence plots. So basically median income, and that's the partial dependence. So it looks like something that increases linearly and then saturates a bit here. That's normal. So that's as we vary the median income, that's the effect on the value of the house. So being a linear curve here does not mean that the relationship is linear. The effect's linearly increasing. Okay, if it's a flat curve like this, then it means that the effect's linear, like the one between house age. That's small, a little bit below zero, but it's flat, so it's a linear relationship. We can always say that average rooms is almost linear, but median income is increasing. The effect's becoming higher and higher as the median income gets higher. And here's the effect of average occupancy. It has a larger effect in the beginning, but in the end, it has a smaller effect. Okay, so this is kind of univariate PDP. Okay, so we can look at like 2 dimensions. So we plot house age and average occupancy, and here you have the effect on the prices. See, and here you can see nonlinearity kicking in. Okay? We can also plot, for instance, like a map of California, and clearly you see where the effects are. The larger is close to the ocean and close to the big center, like San Diego and LA. Okay, and if you get closer here to the desert, then you have a less impact. And if you get further here, you can have even negative effects on prices. Okay, so this really show the nonlinearity kicking in. Okay, so it's not a linear relationship between the location, geographic location, and prices. Okay? So that gives an idea of what's going on. This is a kind of the final tree is a kind of a sequence of smaller trees estimated by boosting. Okay? One question: how we define the variable importance with boosting. This is our question number 2 for our live session on Friday. Okay, think about this point. This is boosting. So the idea of boosting is that we want to compute a tree, a nice model. So our model will be a kind of a sequence of small trees. And this combination of trees will give a lot of nonlinearity. Okay? Now, what we are going to do with bagging, which will have the random forest, instead of having a sequence, this is estimated in a sequence, okay, of trees, we are going to construct several trees in parallel, but big ones. Big trees in parallel. Like here is a sequence of bushes, okay, of small trees. those very small bushes. And with bagging, we are going to put a lot of trees, big ones, in parallel. And basically, instead of taking the sum, we are going to take the average. That's what we are going to do. Okay? So what's the algorithm? We have the data. That's the bagging algorithm. We draw a bootstrap sample, okay, of size t of the original data. We are going to do that by sampling with replacement. Okay. For each sample, we are going to estimate a tree. Okay. And this estimated tree will be fully grown. And with this estimated tree, we are going to make predictions with the original data. So we are going to have a prediction for each tree. The final prediction will be the average of all these predictions of each tree. Okay? What's the intuition for that? Imagine that each tree, okay, is unbiased, has zero mean, and the predictions have variance sigma square. Okay? Each tree B. And we are taking the averages of these trees. And we want to compute the variance of that. Okay? And we are assuming that each tree is independent to the other. Okay? So basically this will be 1 over B2, B times sigma square. This will be sigma square divided by B. So basically taking the averages, we can reduce variance. But for this to be true, we need this to not have like covariances. We need one tree to be very different from the other. And the problem that just doing the bootstrap is not enough, okay, to have one tree different to the other. So what we are going to do, at every decision, at every split, okay, we are going to look only to a subset Q out of the P possible variables. So we are going to randomly select out of my basket of variables only Q out of P. And we are going to look for the best split only using these Q variables, not the P variables. And we are going to do this randomization for every single split. So in the end, we can have trees that are completely different from one to the other. Okay? So they are really like forcing the trees to be independent. And then we are taking the averages of the trees. Okay? And these trees are large, so no pruning involved. So our final prediction of the random forest is just the average. Okay? Usually you can also try to see how many trees you estimate, how many bootstrap samples. You can look at like an out of sample experiment, basically something around 1,000 will be more than enough and will work fine. My experience that changing these won't change much the results. Okay, so why it works? So imagine that we have this function here, f of x. So this I'm plotting the blue dots. It's the observations, okay, the y's against x. And suppose that I come here and fit a tree randomly, random tree. I decide that I have like 1, 2, 3, 4, 5 splits in a tree. And I randomly fit that. And I get this red line. Okay? The fit is really poor, right? I think you all agree with me that just a horrible model. Now imagine that I come here and I fit another tree. Well, pretty bad still, right? Very bad. A third model, not good either. Some other models, all very poor. And I continue and I fit like 1,000 models, and that's what we get. Okay? So after 1,000 models, none of them are really good, but then I come here and I'm taking the average of the 1,000 models. And whoa, it's much better than every single model. And at least it starts to get the shape of the function. And this is just with 5 splits. So let's make like 10, 20, 30, or 50. And then you can see that the fit is pretty good, right? With 50, 30, you start getting, even with 10 already, you get like the form of the curve. So we are really approximating, and here is just like random splits. So it's saying, okay, take the 50 random splits of the data, fit a local constant model in each region, do it 1,000 times, takes the average, and bingo, you fit the function. Okay? The only thing that looks strange, but you're going to answer me why, that's another question for our live session, why the model saturates in the extremes, why we have these constants on each extreme. Okay, that's another question for our live session on Friday. Okay? And comparing random forest with boosting with the California housing data, for this specific data set, boosting is a bit better, not very, it's on the second decimal place, but it's a bit better than the random forest. Okay, the difference between the random forest is related to the number of points that we allow in each terminal node, instead 2 or 6. Okay, and but so the best random forest gives us an error that's around 0.36, and the best boosting will be something approximately 0.34. Okay. Right? So that's it for today. The rest of the slides are about like consistency of random forest. Okay, I'm not going to talk about it; it's a bit too much. But we have the slides, we have the papers on our Google Drive. So anyone interested, I'll be more than happy to discuss with you. Just drop me a note. We can have an appointment over Zoom and we can discuss that. Okay? Thank you very much. See you on Friday.